Hi everyone, Mr. Schleicher here with another chemistry video. You already learned how to write and name ionic compounds, writing those formulas and then reading the names of those formulas. But things can get harder than what we've already seen. Today we also are trying to look at these harder scenarios and learn how to deal with them. So the two things you should learn from today's lesson are how to read and write formulas of transition metal ionic compounds. So transition metals, the charge it can vary. It's very interesting to deal with. And then your other goal should be how to read and write the formulas of polyatomic ions in your ionic compounds. So let's go ahead and begin. We're going to learn about binary ionic compounds first. Binary just means you have two different elements in there. They're going to be your cation, your positive cation, and your negatively charged anion. And we're going to deal with a situation where they have a variable metal charge. A variable just meaning it's a transition metal and the charge could change. It could be +1, -1, whatever. Rare transition metals, if we look at our periodic table, are right in the middle of that periodic table to the right of the first two columns and then to the left of that zigzag line there. Because they have more than one possible charge, that's what we call them, a variable charge. And then we're going to have to use some special knowledge here, or some special notation here. We're going to use Roman numerals to indicate what charge these metals have when they are in a compound. So the Roman numerals do indicate that metal cation charge. You only use it in a situation where you have these variable charges. Now as review, here are the Roman numerals. 1, 2, 3, 4, 5, and 6. That's only up to what you have to know for this class. So I, 2I, 3I, IV, etc. And that's what they look like. Now, the metals that do not require Roman numerals are all your metals that have a fixed charge, your metals that are always the same. So that's going to be your group 1A metals. They're over there on that first column. They always have a +1 charge, so you don't need a Roman numeral to tell the charge of that. Now your group 2A metals, very similar. When they are an ion, they are always going to have a +2 charge. So everything in that second column there in your periodic table, if they're in your ionic compound by themselves, they're +2. You don't need a Roman numeral for those. There's these three other metals that are always going to have the same charge in ionic compounds. It's going to be aluminum, Al, which will always have a 3+ charge. Then you will have Zn, zinc. That's always going to have a 2+ charge. And then you will have a third one, Ag, which is silver, and that is always going to have a +1 charge. So you'll also notice that these are in groups like 3A for +3, 2B for 2+, 1B for 1+. And some other trick that I like to use is these three elements also kind of form a staircase. So the first staircase is step 1 is 1+, step 2 is 2+, step 3 is 3+. So you can always remember those three metal cations as having those charges. Since you know the charge, they don't need a Roman numeral. Everything that needs a Roman numeral is every other metal. If it's non-group 1A or 2A or those three metals, all of those metals there, you need to have a Roman numeral in the name. We're going to learn how to figure out what Roman numeral it is, but just remember that your total number of charges always has to equal 0 in your ionic compounds. When you write out that ionic compound formula, they have to equal 0. When you look at a formula, those charges better add up to 0 or someone wrote it out wrong. So first of all, let's just try to learn where these Roman numerals come from by looking at an ionic formula and then trying to tell the name of that. So Mn, that's manganese. If you look at the periodic table where manganese is, it's right there in the middle where all those metals that we don't know the charge of is. So what you have to do is kind of make a logic puzzle. You have to figure out what manganese's charge is based off of the other one. So that O is oxygen. It's in group 6A, so it's going to have a 2- charge, so O2-. Now we know that Mn has to cancel out 2-. So what added to 2- is equal to 0? Well, it's going to be 2+. So that means Mn is going to need a 2+ charge in order to cancel that out, which means we're going to use a Roman numeral of 2 in the name. So that name is going to be manganese parentheses, Roman numeral 2, space, oxide. We definitely use just the element names there. Now remember from last lesson, we do change that oxygen. We change the ending to end it with an "ide," so that's where oxide comes from. Let's look at the next example here. We have Cu3P. So let's look for Cu. Looks like that's copper here. Looks like it has a variable charge again. So we're going to have to figure out what charge it has in this ionic compound. So we can get those clues from that P there, P being phosphorus. Phosphorus is in group 5A. So if it's in group 5A, it's going to have a 3- charge. These are really easy shortcuts. We have 1- from 7A, 2- from 6A, 3- from 5A. So we look at phosphorus, we can see that we have a 3- charge. We have two of those 3- charges. So if you have two 3- charges, think about what that adds up to. That's going to add up to an overall 6- charge. So you have to think to yourself, okay, if I have an overall 6- charge, how is 3 of my Cu's going to cancel it out with a positive charge? 3 of them add up to 6+ somehow, because 6+ is going to cancel out 6-. So think about, okay, basic multiplication. 3 times 2 is equal to 6, so it must have a 2+ charge. And remember, we're learning all of this based on the logic that all your charges have to add up to 0. So Cu has to have a 2+ charge. Since we know it has a 2+ charge for everything to be balanced, then we know that our Roman numeral is going to be 2. Now remember, Cu, that is copper. So our name here is going to be copper, and then Roman numeral 2 in parentheses. And then we had phosphorus. So remember, we changed the ending of phosphorus to "ide." So we're going to name this phosphide. Okay, next example. We have this Cu2Se. We know Cu means copper, but we still don't know the charge. Se is selenium, so we're going to look for that in the periodic table. Se right there. It's in group 6A, so we know it has a 2- charge. So we can use that to help figure out the Roman numeral of Cu here. So Se is 2-. There's only one of these 2- here. So that's an overall negative charge of 2-. Now Cu, there's 2 of them, and 2 of them have to cancel out that 2-. So 2 of what charge would cancel out 2-? So 2- and 2+ would add up to 0. So 2 of what adds up to 2+? So 2 of 1+ adds up to 2+. So Cu must have a 1+ charge, which means that Roman numeral for copper is going to be 1. Now we have everything that we need to write this name. I wrote out Roman numeral there, and we'll combine everything that we have. Selenium, just keep that first part there, selene. Since it's the last part there, we are going to end it with "ide." So copper 1 selenide should be our name of this ionic compound. All right, next example. Let's look at the CO2S3. CO doesn't look like a metal to me, or like a metal with a known charge, but it's right there in the variable charge section. Cobalt is CO. So cobalt has some unknown charge, so we have to figure out that unknown charge. And then we're looking at sulfur. Sulfur has a 2- charge, so cobalt and sulfur are combined somehow. We have to figure out the Roman numeral of cobalt. So there's 3 of these sulfurs, 3 of these S's, and each of those has a 2- charge according to a periodic table. So 3 2- add up to a 6-, and we need to cancel out that 6- with 2 of these cobalts. So 2 of what charge is going to add up to 6+? That is what we're figuring out here. So 2 times what is equal to 6 is how we can think of that as well. And that's going to be 2 times 3+ is going to equal 6+. So we have a CO3+. 3 is going to be our Roman numeral. And remember, CO, the name of that was cobalt. So we have everything we need to name this compound. Cobalt, 3, I was about to say 2. Sulfide. Don't forget to change the ending to "ide" for that nonmetal. Okay, last example of figuring out the Roman numeral here. Now we have PB, peanut butter. We have O. We know O is oxygen. So PB is randomly all the way down there. It's lead. You can see the name there. It used to be, it's PB because the old Latin name for lead was plumbum because they use it in a lot of plumbing. But lead is in that unclear variable charge area, so we're going to have to figure out that charge, that unknown charge of PB. So let's use oxygen to try to figure out what that charge is. We know O is in group 6A, so it is going to have a 2- charge. So O2 minus, there are two of them. There's two of these 2- charges. Therefore, that's going to add up to like an overall 4- charge. When something adds up to overall 4- charge, in order to add up to 0, it's going to be canceled out with an overall 4+ charge. So one of these PBs has to add up to 4+. Very, very simple problem here. If you have one thing that needs to add up to 4+, that one thing is going to be a 4+. So we know our Roman numeral, it's going to be 4, and PB is lead, so our name is going to be something like lead 4 oxide is what we're looking for. Don't forget how to write the Roman numeral for 4. It's that thing where you put the I before the V because it's like 1 minus 5 is 4. So lead 4 oxide is the name. Okay, let's try to have some practice here where now we are looking at the name of our compound and then we have to write the formula. So the trick here is remembering that all of your chemicals, all the charges of all your ions, they have to add up to 0. And the other thing here, a lot of people, they make this mistake. Please do not be one of the people who make this mistake. The Roman numeral in the name, the Roman numeral does not mean the number that you have of the element. The Roman numeral is not the number of the element. Sorry, I messed up my video here. But the Roman numeral is equal to the charge of that metal. Remember that. The Roman numeral is a charge. It's not the number of that element. So we just have to track the charges and make sure that they add up to 0. Then we can figure out the number of each element that's going to be in our formula. So let's look at this first one, gold 1, nitride. Nitride, just look for the beginning, nitrogen, it's actually nitrogen. So nitride is going to be an N with a 3- charge. So we know there's an N with a 3- charge, and then we're looking for gold on the periodic table. We need to figure out our element symbols for this situation. Gold is AU, so we are going to put an AU. Now it has a Roman numeral of 1, so that 1 means it's a plus charge or a 1+ charge. So you have to think to yourself, okay, how many of each ion do you need to cancel each other out? You have 1+ and you have 3-. So I'm already thinking to myself, okay, I'm probably going to need 3 of those 1+s to cancel out a 3-. And that is indeed the case. You need 3 of those 1+s to cancel out a 1-. So in your formula that you write out, you are going to write 3 of the AUs and then 1 of the Ns. So your formula is AU. Oh, I made a mistake in the video. Gold is AU, so it should be AU3N. Ignore that G. That's actually, I accidentally wrote silver there. Copper 2 oxide, let's look at this next example. Copper 2, that is Cu2+. That Roman numeral 2 means it's a charge of 2+. We know oxide is 2-. So you look at both of those and you just have to ask yourself, do they cancel each other out right away? And the answer is yes. If you have a 2+, that cancels out 2-, so you just need 1 of each. Therefore, your formula is going to be CuO. For this next question here, I kind of forgot what we were talking about. Oh yeah, tin. So we're looking for tin on the periodic table. Tin's is Sn. So if you look for Sn here, it has a Roman numeral of 4, so it's going to be Sn4+, that's a charge. Sulfide, it's in group 6A. We saw that before. It has a 2- charge because it's in group 6A. So you're going to need probably 2 of those S2- to cancel out that 4+. So your formula is going to be SnS2. The video got cut off a little bit here. I apologize for that. So just looking at these 3 answers, that's how you write the formulas from. All right, let's go ahead and talk about our the names there. Non-binary ionic compounds. Non-binary ionic compounds. Non-binary means you have more than two elements that are bonded um, in your ionic compound. But you still only have a cation and an anion part. It's not like you have a bajillion ions going around. It's just cation and anion. A positive thing attracted to a negative thing. And that forms your formula. So how this actually occurs is we have things in the world called polyatomic ions. Polyatomic just means poly is multiple, atomic means atoms. So you have different elements that are bonded together. So in this like reference materials grouping, you do have a list of polyatomic ions that you can reference. Over here on the left, this page is available on your Canvas page on your chemistry reference materials, something like that. And these are all the ones that we will try to use in this class at least once. On the left, you have the name of the polyatomic ion, and on the right, you're going to have the formula and the charge of it. So notice that like the whole thing stuck together, and there's a charge in the top right. And then within each ion, you basically just have a certain number of each element there. So in terms of looking at the formula and trying to name it, if you have a metal in the polyatomic ion, you just say the metal name and then the polyatomic ion right after that. Remember, if there's a Roman numeral, you have to include that. If you have a polyatomic ion and a nonmetal, don't forget to put that I at the end of that nonmetal, but it's just the polyatomic ion name and a nonmetal, and I. If you have a polyatomic ion and another polyatomic ion, you just say both names next to each other as is. So now we're going to look at that first example here, and we did have, I think it skipped ahead before I saw, but we do have an Na, which means we're not going to look at the Roman numeral. And then we have this NO3. NO3 is on our polyatomic ions list. Na is sodium. NO3, we can look that up really quick. I got a little lost on my iPad here. NO3 is down here. We see it's NO3 minus, and it is called nitrate, N-I-T-R-A-T-E. So the name here is sodium nitrate. Next example, we have NH4 and we have Cl. So you might be confused, like, oh, where do I separate this? You just get a feel for it, and you look up on the polyatomic ions list, like, what are the actual things bonded together? So NH4 is called ammonium on our list, and then we're going to look for Cl. Cl is chlorine. Since it's a nonmetal, we are going to change the ending there. The ending of that name is going to be changed to "ide." So we're going to call this ammonium chloride. Next example, now it looks like we have a lot of different elements there. So these are two polyatomics. We're going to look both of these up. NH4, we already know what that is. That's ammonium. And notice it's in parentheses there. There's like two of them total. So you see a parentheses surrounds the entire polyatomic ion. And then we also have a 2 on the outside on the bottom right. That means we have 2 of those ammonium polyatomic ions. So next part here, we're going to go to the polyatomic ions. Let's see, what was the second thing we were looking for? We were looking for sulfate. So sulfate, SO4, 2 minus, is what that SO4 is. So we just say ammonium sulfate, and that's the name here. Next one, we have FeCO3. Fe, we look for that metal. Oh, darn, it's one of those variable charges ones. So we have to come up with a charge with the Roman numeral of that Fe, of that iron. We know the name is iron, but we need a Roman numeral. So we have to look at the other part of our formula to figure out what that Roman numeral could be. CO3, let's look that up on our polyatomics list. It looks like CO3 is up there. CO3 2 minus is carbonate. It is a 2 minus charge, it's really important. So if we have carbonate, CO3, and it's a 2 minus charge, and there's one of those, and there's one of those Fe's, then to cancel it out and add it up to 0, we're going to have iron have a 2 plus charge. So our name here is going to be iron 2 carbonate. All right, those are some examples there. Last situation, let's look at a name and try to come up with a chemical formula. So most importantly, balance your charges. Your total charges should always have to equal 0. So your positive charges added to your negative charges have to cancel out. That's what that means. If you have more than one polyatomic ion that you're trying to write, make sure that you put that ion inside parentheses. Otherwise, things get really weird. So let's look at this example. Potassium hydroxide. Potassium sounds like an element, I know, and indeed it's right there. It's K, and it has a 1 plus charge, so keep track of that. K has 1 plus, so we're going to write that down to keep track. And then we're going to look up hydroxide. Hydroxide does not sound like an element. I've never heard of a hydroxide element. So I'm going to look at my list of polyatomic ions. It looks like hydroxide is OH minus. So I'm going to write that down, OH minus or 1 minus. And it looks like we just need one of these Ks and one of the OHs to write out this formula. So we are going to write that out as KOH, just written together like that. Next example, ammonium. We know what that is. We wrote that down a few times. It's NH4 plus. Now phosphide, remember, that is going to be that phosphorus and with that 3 minus charge. It's just like, instead of ide, it's phosphorus. So NH4 plus, how many of those cancel out a 3 minus charge? It's going to be 3 of them. So you're going to put that whole thing in parentheses, NH4 3P is your answer. Next one here. Now this is a little bit different. The ending is not ide anymore. Be really careful there. Ammonium is still NH4 plus. When I just have a plus, you know, that just means 1 plus. Now I remember I was looking over here and we actually do not have this polyatomic ion. So I want you to change your answer here. I said it was phosphite, but let's go ahead and use, I was trying to remember what phosphite could be, but let's go ahead and use phosphate instead. So phosphate, you see it on like right there under the P's. That's going to be PO4 3 minus, and we can keep track of that and write it out in our name here. So PO4 3 minus is our polyatomic ion, and again, you need 3 of those plus charges to cancel out a 3 minus charge. So you're going to have 3 NH4s in your formula there. Next example here, gold. We're going to change bromate to carbonate. We don't really use bromate in this class. Remember, gold is Au, and the Roman numeral of 3 is not the number of Aus. It's a 3 plus charge. And then chromate, sorry, not chromate, carbonate is way up there. It looks like we looked at it before. It's a CO3 2 minus charge. So CO3 2 minus, you have to think to yourself, oh my goodness, how many of each do I need to cancel each other out? This is a problem we've kind of seen before. Now you just have to think to yourself, 2 3 plus charges will cancel out 3 of these 2 minus charges. So you're going to have 2 of your gold. I made a mistake in the in the answer there. You're going to have 2 of those golds and 3 of the carbonates. So it shouldn't be Cu, it should be Au. And we're looking at the next one here is silver. Silver chromate, so CrO4 2 minus. CrO4 2 minus. Silver is something that you memorize. It should always have a 1 plus charge. You need 2 silvers to cancel out that 2 minus charge. So there we have it. That's how we write the formulas all there. I know I went really fast at the end there, so go ahead and pause if you got lost anywhere and ask me any questions in class. Thanks for watching.